like we said, the variation of g will then be equal to this. After having the term I just talked about to be equal to 0, like I've said, you can just revise this video or the previous one. A few seconds and you'll see that. Next, we are going to be talking about the variation of the action I sub f, which of course, if you remember, was what we have already itemized or labeled from here. So what we have done so far was simply to have obtained the variation of what we call I sub g. This is I sub g. And now we want to work on I sub f. I sub f. And now this is the variation of I sub f. Now that's what we're looking at. Now take note of this. Right from the beginning in our variation of I sub g, we didn't list or mention anything about what variables we choose to vary the action with respect to. But now you can see in the end that it automatically comes out with this being the variant, or g mu nu being the variable with respect to which we are carrying out this variation. We didn't even mention it or say that that's what was going to be our parameter or variable right from the beginning. So it will only make sense that in our varying I sub f, we use g mu nu as our varying parameter. We will assume, of course, that this function here, or I sub f, is not a function of any derivative of the metric tensor above the first derivative. And so that's why in our varying I sub f, it is with respect to g mu nu and its derivative. And so this is what we have done here, just like we will do normally, again, just with respect to g mu nu and its derivative, and that's why we have these two terms. Now, in order to rewrite this second term, we want you to look at, just take a look at this expression here. This times this, combined together by Leibniz rule, taking the partial derivative. So it will be simple for us to keep this constant and differentiate this. And of course, the variation, like we've said, commutes with the partial derivative. So because of that, it doesn't matter if we perform the derivative first or the variation first. Now, plus, we're going to keep this constant, but then we'll differentiate this, and this is what we get by the usual Leibniz rule. Of course, what we have here on this second term, which is this, can simply be found, or we can make the subject of the formula by saying this minus that. And that's what we've got here. Now with this then, we simply substitute this back into this. So in place of this object, which we have shown to be this, we simply put this into this place. Now before I go to the next step, take a look at this. You can see that this is all combined and it's all differentiated with respect to x alpha. But this has some object differentiated with respect to x alpha, but multiplied with the variation of g mu nu. Now the first term also is some object multiplied by the variation of g mu nu. So you should just bear in mind that we're going to combine this and this. So in my next step, I'll be saying this minus that, but I'll have a common factor or variable or the variation which will be outside of the bracket containing this and that. And then this, of course, will still be part of the integral. So coming with me here, that's what I've done here. By combining just the terms that I've mentioned, and I have a common variation parameter here, which is the variation with respect to g mu nu. Then plus, of course, the term which is standing all by itself. I can call whatever is in the bracket here some L sub mu nu. And if you notice, L sub mu nu, it means that will be L sub mu nu differentiated with respect to x alpha. And this is an integral with respect to, say, the 4x. And by our Gauss law, this is the same thing as, of course, dispensing with the derivative with respect to x alpha. This is just an integral of L sub mu nu, but now over the surface. Again, because it contains this variation with respect to g sub mu nu, which vanishes on the surface, this integral as a whole is equal to 0. So in my next term, what I'll be left with as a variation of I sub f will simply be this first that I've written as the first term here, this one. So which is what I have here. Now looking at the term here, just to make this easy, but then again, because already someone have done this before and so I know where I'm going, I'm just going to momentarily call this T sub mu nu. I'm not assuming or calling it the energy momentum tensor just yet, but we shall find out that it is actually energy momentum tensor. So if I call what is in this block or square bracket minus 1 over 2 T sub mu nu square root of minus g, it means that what I'm left with, okay, I think I made a mistake. This shouldn't be that. this should be 1, and it should have an integral, by the way, 1 all over 2c minus 1 over 2c, and this should be the 4 of x, just as it should have been there. Oh no, okay, also I missed something too. It's no problem, we can just make that all. So from before I do that, I think I remember what I've written there. So it simply means I have here with me, okay, I got that right in the next step. So this is g mu nu, the 4x, that. So I made a statement, so from this, the variation of this being equal to that plus that equal to 0. And you can see that, of course, I have this multiplied by that, but I've said that is what is inside this square bracket that I've named this. And of course, everything else follows me as it should, and that is what we've got. Again, remember, we are not saying individually that this is equal to 0 and that this is equal to 0. It's actually the sum of the two, which gives us a complete action with respect to which, when we vary, we obtain 0. And that is what I've got. So I will have to add the 2. Now, this is the second one, which has to do with variation of I sub f, and this is what we've got. The first one, which is variation with respect to I sub g, is what we have already shown from here to be equal to that. So I simply just reiterated the whole thing, and that is what I get. Now again, looking at this expression, I simply just factor out this, I bring out this factor, and then leave everything else inside. I have variation with respect to g mu nu and square root of minus g to be common to the two integrals, and I pull it all out. And so when I pull out this factor, it means I will have something inside to compensate for it. For instance, of course, if I were just to evaluate or open up this bracket, this will cancel the 4 c's that is here, and I'll be left with 1. And then this 16g and 16 pi g will cancel that, and there will be nothing on top. Of course, the 2 remains where it was as it is, and that's what we get. Okay, now from this, again, we can see in total that is the variation of I, which we've obtained to be this compact object, which is equal to 0. Now, for arbitrary variation of this g sub mu nu, whatever is left here has got to be equal to 0. Of course, combined with this, but then it's so inconsequential because we can just divide that out. So we've got this to be equal to 0, and if it is equal to 0, evaluating it, this is what we get. Dividing the 16 by the 2 below over there gives us 8. Taking it to the other side gives us a plus, and this is what we get. And this is the Einstein field equation. And if you remember, we called g sub mu nu to be equal to this. That was what we called it right from the beginning. And this is the Einstein tensor. And looking at this tensor now, of course, we remember our Bianchi identity. The Bianchi identity, or what I call the contracted Bianchi identity, gives us that this is equal to 0. It means when I raise the tensor mu all over the place, of course, as the whole expression, and I contract the left-hand side especially with respect to mu, then taking a covariant for divergence, this gives me 0. Then the same must be true of the right-hand side. In other words, this is all just some constants. If I raise mu here and take the covariant divergence of that, I should get 0. Beginning to sound familiar? This is also one of the properties of the energy momentum tensor. Well, now moving on, we remember that T sub mu nu necessarily has to be symmetric. It has to be symmetric, first of all, you can say, because the right-hand side too is symmetric with respect to the interchange of mu and nu. The Ricci tensor is symmetric. We have a Ricci scalar here. The what else do you call that? The metric tensor is also symmetric with respect to mu and nu. And besides, from our definition of this T sub mu nu, which was what we have obtained or identified right from here, we can see that this is purely a function of just maybe some metric tensor and its first derivative, which again is symmetric with respect to interchange of mu and nu. And if that is the case, it simply means that we have been able to deduce that this T sub mu nu, which we named that object over there, is conserved in the sense that when you take the for convergence of this, for divergence of this, covariant divergence of this, we get 0, and it's also symmetric. And these two are very important properties of the energy momentum tensor, unless, of course, for their non-uniqueness. So, as usual, this is still not unique, as we have said in our lecture 1C or 1B and C. The energy momentum tensor, which we identify in here, is still not unique because when you add again an antisymmetric object in two such indices with respect to which you'll be differentiating, this again, the whole object as a whole itself is going to be conserved. So, based on these two properties, we identify this expression as the energy momentum tensor. Okay, moving very quickly. As we remember in classical electrodynamics, we have that the Lagrangian in that case, of course, for free charges, we're talking about vacuum in this case, no charges. We have that L is equal to minus 1 over 16 pi f sub alpha beta f alpha beta. Of course, I can decide to lower. Now that brings me to a very important point. In order to solve this, because it means I will have to substitute this into this expression to find the energy momentum tensor, which we shall do in a moment, and hopefully that wouldn't be any much problem. But then, I need to say this because given the fact that we are going to be substituting this in this expression, the Lagrangian for classical electrodynamics, obviously you can see, if I lower these two indices, using mu, G alpha mu to lower alpha, and of course that will give me a mu here, and using G beta nu to lower beta, I'll get a nu here. I have this Lagrangian to be purely a function of just the metric tensor and not its derivatives in any way. So L is equivalent to just something which is a function of the metric tensor, not even its first derivative and not the second derivative. And because of that, for classical electrodynamics, this part of the energy momentum tensor as defined by this, which was obtained from the variation of the action which is ascribed to the other fields, this part of it is 0. So for classical electrodynamics, what we have to be the energy momentum tensor as derived from this expression is simply equal to this being equal to that. Since the Lagrangian is independent of any variation, any derivative of the metric tensor, this part is 0, and so this is equal to that. Now the other point is in that lecture 1B and C, I think I can erase somewhere here. Hopefully this won't cut in a few moments. So in our expression there, when we wanted to, we realized we are going to be differentiating the Lagrangian with respect to some A alpha. So A alpha actually, what we had to differentiate with, so I maybe lowered that, something like that. I just had the Lagrangian to be written in this form, alpha beta, opened it up. And of course, if you recall what this will give me, let me just get a picture of what the first term would be like. A beta, and then the other one should be alpha A beta. The ordinary thing to do is when you want to differentiate this object, for instance, with respect to that's with respect to this. Let's say let's call this some f, and what you want to do is some the f, the a sub iota kappa. The normal thing some people will do, of course, is still correct, is to lower these two indices with two metric tensors. And then, of course, when you do that, both these objects here and this will sort of look like that. And so the differentiation will go on easily. Well, not easily, actually. In fact, with more elaborate work, a little more tedious than what we did the previous time. And that will be quite all right. But you have to be careful to know what metric tensor you use to lower what, and then to remember to use that to raise them in the end. And then that is that for the derivation. But it just means it's something that could be done quite easily. We are going to be doing something here that wouldn't require that here at this moment. So sorry for that aside, and I hope it doesn't obscure what I'm about to do next. But very simply, so far, where I stopped was to say that this, for classical electrodynamics, is equal to that. And having expressed and talked about these objects here, I think it's about time I'm going to erase this part. And in fact, so very quickly, in this expression, well, let's try to see how we can make that a little bit more manageable. This is going to be d of L square root of minus g, dg mu nu. I can decide to keep this a constant and differentiate that, in which case I'll have some minus to that minus g dl g mu nu, and then I have here with me some minus 2 all over square root of minus g. L is kept a constant this time, square root of minus g, and this is going to be dg mu nu. So the typical Leibniz rule is all we've done. We keep this a constant, differentiate that, and next we differentiate this. We keep this a constant and differentiate that. This gives us that, and further what I'm going to have is simply minus 2 dl the g mu nu. And the second term over there I can write as this square root of minus g L, but then this is going to be square root of minus g. Okay, I think what I would like to do, by the way, should be to say that this is the same thing as saying the g mu nu, then the square root of minus g, the g. Okay, really, I'll outline that over there. So, yeah, exactly. So this is the same thing as that. Looking at this expression, of course, what I would like to do is next to take note of that, but maybe very simply, in order not to let it disturb what I'm about to do next. The square root of minus g, the g, it should be the same thing as here, minus 1 over 2, because of that half and the minus here. It's still going to be 1 over the square root of minus g, I'm guessing. That's what it should be, if I differentiate that with respect to that. So this means that C mu nu, and still remember that this is just for classical dynamics, especially for the Lagrangian we have chosen. G here, mu nu. And this is going to be minus 2 times the Lagrangian, all over the square root of minus g. And then I have here with me some the g mu nu, but then multiplied by some minus 1 all over 2, 1 all over square root of minus g. This, of course, cancels to give us a plus, and this will again be minus 2, the L, the g mu nu, plus, I've got here these 2 multiplying. When they multiply, square root of minus g times square root of minus g gives us back another minus sign, and then it gives us 1 all over g, L, but then I've got some the g mu nu. Well, the g mu nu is what we have obtained before, and especially our first lecture, and this is equal to minus g sub mu nu, and so in essence we obtain this to be equal to minus 2, the L, the g mu nu, and this is minus 1 all over g times L, but times minus g mu nu. Okay. At this point, then, it's obvious that what we are going to obtain is this cancelling that. So minus 2, minus 2, the L, the g mu nu, but then plus g sub mu nu L. So let me put that on top, and this is what we've got for the energy momentum tensor. So T sub mu nu being equal to minus 2, the L, the g mu nu, plus g sub mu nu, the L, as L. So take note of something here. In the previous expression, in what we did in lectures 1, B, and C, we had to differentiate with respect to A. Our variable was the four momentum, not the four momentum, the four potential, well, A or four vector, that's what we call that. But now we are here differentiating with respect to metric tensor. And that is what we're going to do. So the only problem, really, if it is a problem, is this derivation here, the differentiation of that. And I would like to perform this differentiation. So, of course, one mistake one cannot make is, if you see, I've been careful to write this expression. So let me just write L. L I've written to be equal to minus 1 over 16 pi G. I guess what I've got in there is, yeah, alpha, beta. I'm coming. I'll just give a moment to explain how I came about with that expression. Mu nu, but then I've got here alpha mu, and F over there is beta nu. Okay, so like I was saying, I guess I didn't say much about that. Excuse me. Minus 1 over 16 pi F sub alpha beta F alpha beta is equal to minus 1 over 16 pi. So we talked about using G alpha mu to lower beta and G beta nu to lower beta. To lower alpha and then to lower beta respectively. Now I performed an interchange between beta and nu. Doing that gives it to me in this form. It's tempting at this point to think that, well, I can just differentiate this with respect to G sub mu nu, which is here, and it will simply mean that this disappears, And all I'm left with is the expression or the solution that says that the derivative is equal to simply minus 1 over 16 pi times this with this absent. That will be wrong. And remember, because first of all, in performing this kind of derivative, you are supposed to perform with respect to a variable which has completely different indices from what is already contained in the Lagrangian. For instance, in this case, I would like to perform this with respect to G rho sigma. Yeah. G rho sigma with the intention that in the end, I'll change rho, for instance, to mu and sigma to nu, and then obtain it in the form that I can substitute in the expression here. But first, for the derivative, I cannot do this or substitute this exactly the way it is into this expression. So if I want to substitute this exactly into this expression, I will have to change this to this. So that what I can do is say that this is the same thing as minus 1 over some 16 pi d the G rho sigma of G here, alpha, beta, G mu nu, F alpha mu, F beta nu. Okay, now at this point you can see that by Leibniz rule, what I'm going to get is some differentiation of dg alpha beta, dg rho sigma, G mu nu, F here sub alpha mu, F beta nu plus. I leave the first one a constant, the G here mu nu, and the G here rho sigma, F again alpha mu, F beta nu. Okay, of course, differentiation with respect to this, these are not functions of the metric tensors. Their derivative with respect to that will be 0. So we simply ignore that. In our next step, now you can see the usual problem we have. This could have been, for instance, say the G beta alpha and the G rho sigma, or the G sigma rho. In other words, because of course the metric tensor is symmetric with respect to the interchange of these two. So you cannot for sure, for instance, say that this is the same thing as say the Dirac delta of alpha rho and Dirac delta of beta sigma. In other words, that when alpha is equal to rho and beta is equal to sigma, this expression is equal to 1 and then 0 otherwise. Because again, like I've written it in this form, it might as well could have been beta rho and then alpha sigma. And anyone could have done that. Again, this also could have served. So if you remember what we usually do, and we have done this quite a lot, we will have to symmetrize by averaging over these two forms. In other words, the derivative of this with respect to that will have to be written as the half, that's by symmetrizing, the half of this plus that. So keeping that in mind, sorry I wouldn't dwell much on this because there's a separate lecture in which we already did that elaborately. Feel free to go back in case you feel lost here. But proceeding, this is alpha rho, this is beta sigma, plus again beta rho, and then this is alpha sigma. And now I have, okay, well, I'm not going to do away with the G mu nu. G mu nu, F alpha mu, F beta nu. And next I've got again with me plus here. So I'm going to have half here, Dirac delta, chronicle delta, sorry, rho. And then chronicle delta nu here sigma plus nu rho mu sigma. And then the next thing I'm going to have is G alpha beta, F alpha mu, F beta nu. Okay. Now, just a little more hard work, not so much, but a little. Okay, I'm going to pull out the halves that is in them all and put it in here to be sort of, so I'm guessing this will be 32 pi. Now with this given, you can see that if I were to multiply this with this, I'll just do that straightforward. Wherever I see, I'm guessing I'm going to have to change only alpha and beta because I don't have rho and sigmas here. So first of all, G mu nu is untouched by the chronicle deltas, but alpha has to change to rho. So the alpha that was here becomes rho mu. And then F here, the beta has to become sigma nu. That's for the first time here, evaluating out, or yes, just evaluating the chronicle deltas on that term. And plus for the second time here again, G mu nu comes along for the right, still again untouched. My alpha this time becomes sigma, and I have a nu here. And then the beta this time becomes rho, and I've got here with me, yeah, the nu also. Sorry, this is a mu. I hope I didn't make that mistake. Okay, next I have with me plus. The same thing happens over here. At this time around, it means the G alpha beta again is untouched. But I will have my mu changed to rho. And then I have my sigma. Not sigma, sorry, the nu. So this is going to be beta. The nu becomes sigma. And then plus, I have again G alpha beta. Then I have here F. This alpha is untouched. The mu there, however, becomes sigma. And then F, you can see also that this will change the term here. What is it exactly? Sigma mu. So I changed that to mu already. So what I've got is nu, which has to be rho. So first of all, beta is untouched. But then the nu there becomes rho. Okay, well, let me just go through this one more time. I hope I wasn't being too fast. G alpha beta, you can see, is untouched because these conical deltas have nothing at all with the change of alpha and beta, so we just write them all out. For the first time here, it means wherever we see mu on this, we change it to rho, and that's what we have done for the first one. Alpha again remaining untouched. And wherever we see nu, we change it to sigma, and that's what we've done. And beta is all over there again, plus. Again, for the second time, we have G alpha beta, which is untouched. But then I have F sub alpha mu. And then it means that mu here has to be equal to sigma, otherwise this expression is 0. So I have F sub alpha sigma, and then F sub beta, instead of nu, then I'll have to write that as rho. Okay, this is what I've got. What I can try to do is see how to combine them. These two have the same metric tensors. Is there any way we can do that? For instance, I can't, for instance, say, I can here, for instance, say, let mu interchange with nu. That can happen because nu's are dummy indices. I wouldn't have been able to do that for the rho and sigma because they are not dummy indices. Now, looking again at this one, is there any way by which I can make that look like that? Yeah, again, so alpha and beta, so these are the dummy indices, and then alpha, sigma. So I can decide here again to interchange alpha and beta. And so if I did that very quickly, I don't think I would like to be redundant. Very quickly, if I did that, note that I'm going to have G here to be nu, G nu mu. Excuse me. G nu mu and not G mu nu. Anyway, but again, it is symmetric with respect to the interval. So G mu nu or G nu mu is still the same because the metric tensor is symmetric with respect to the two indices. So in other words, this will still be G mu nu, just like this one. But then I'm going to have rho to be attached to nu, which is just the same as this object. And then I'll have nu here interchange or change to mu, which is the same as that. So combining these first two will simply be 2 times G mu nu and then F. Well, we can decide to write it in this form. Okay, I'm being very careful here because let me put it in that form because this is what I've interchanged. Sigma mu and F here rho nu. Plus the next thing again that I was saying, if I interchange alpha and beta, changing alpha to beta and beta to alpha everywhere where it occurs on this term, and the metric tensor remains the same, just like this one, because it's symmetric. Again, but then this becomes beta, so which is F sub beta rho, just like this one. And then again, this becomes alpha, so this becomes F sub alpha sigma, just like this. So I'm going to have 2 times G alpha beta, F here, this will be alpha sigma F beta rho. That is what I will get. Okay, looking at these two expressions, there is something else I can do. First, okay, we can note that we have some common 2. This is minus 2 over 32 pi. Pulling out that, I have here sigma and rho, which are not dummy indices, but I have mu, I have nu. I can, for instance, again, in order to avoid any trouble, because, like I said, I'm trying to make sure that I keep these things all in such a way that they wouldn't affect what I'm using. Anyway, I'm working with rho and sigma, so it's no problem. I can change the dummy indices to whatever I would like them to be. Let me use alpha and beta. In other words, I can change the rho here to the mu. I can just change mu to alpha. and then change nu to beta. If I did that, yeah, so it will correspond with this, and mu being alpha again will correspond with that. I can just do that. And I can do that because they are dummy indices. I can interchange between two dummy indices, just like we've done here, or change a dummy index to something else, but not either sigma or rho because they don't occur twice in any of these expressions. If I did that, having already pulled out these two here, it means I'm going to have 2 times of this expression, but then it will be alpha, beta here. F, this time around it will be sigma, but alpha, and then F here, this will be rho and beta. So in essence, I will have something like minus 4 all over 32 pi, and then multiplying with G alpha beta, F sigma alpha, F rho beta. That's what I'll get. And I'm guessing when we divide these two out, we get 16, and then again, this will give us minus 1 all over 8 pi of G alpha beta, F sigma alpha, F rho beta. Okay. Moving on, let me write that expression out on top. I guess everything else from here down. So what we've just obtained is simply that this expression here is equal to minus 1 all over 8 pi. And we have here G alpha beta. And here F here, subscript sigma alpha, F also here, rho beta. I'm being very careful with the field tensor because the electric field tensor is antisymmetric with respect to the interchange of the indices. However, if I interchange alpha and sigma, I'll get a minus sign. I perform the same interchange here also, I get another minus sign which cancels out. So this is the same thing as minus again still, 8 pi, because the 2 minus signs I'll be getting by saying alpha, sigma, and then beta, rho, cancel. And why am I doing that? So that I can simply say I use this metric tensor to raise alpha. And if I did that, I'm going to have minus 1 all over 8 pi. F, this gives me beta, and this gives me sigma. F here, beta, rho. Yeah. I decided to do this because if I didn't perform this interchange, I will have to be careful what position I place the next object I raise, and for me it's always convenient to put it in this way. So whenever I'm raising, you have to be very careful to make sure that the index you are raising maintains the appropriate position, especially on the electric field, on the field tensor. So now we are going to be looking at what we have next as our energy momentum tensor. So for the energy momentum tensor, what we have obtained so far is simply this derivative. And like I said, if I wanted to make this look like some dl, the g mu nu. So all I'm going to do is simply change what's it called? So sigma was what I called nu, right? So I'm guessing this should be nu, and this again remains beta. Rho I already called to be mu, and that is it. So first of all, someone who may be new to this could get confused. You could say that rho and sigma are not dummy indices. So why am I changing them to things like nu and mu? Note that when I change sigma here to nu, I change sigma to nu everywhere, not just on this term, but on the whole expression. So it changed also in the left-hand side. And the same thing with rho, it changed also on the left-hand side. But remember that since beta and beta here, beta are both dummy indices, I could just, for instance, change them to minus 1 over 8 pi, f alpha, sigma, f alpha rho. And you have to know that this is contracted in the sense that it doesn't occur anywhere on the left-hand side. And so I just change it to alpha, and it's still the same thing with this, without any problem whatsoever or worries as to whether or not my expression is the same. It's the same because it's just a dummy index. But you see that rho and sigma are not contracted. So changing them to anything on any side of the equation changes them everywhere. And so that's how you deal with them. So at this point in time, it just does look like what we have. Again, but still, I will have to maintain on this expression that my Lagrangian is still minus 1 over 16 pi, f alpha beta, f alpha beta. I cannot at will name this f mu nu, because in this expression I already have mu nu. And so because of that, the alpha beta, if for instance it wasn't even mu nu but alpha beta, then what I will necessarily do here is to write mu nu and mu nu or anything else that is not contained as an index in the expression. So at this point, I say that my T mu nu is equal to minus 2 times what have I obtained for the derivative here. And now I have that to be minus 1 over 8 pi F beta nu, and here this is F beta mu. And then again, of course, I have here plus with me here G sub mu nu, but then in the bracket, minus 1 over 16 pi F alpha beta, F here, alpha beta. Okay. At this point in time, we've got a cancellation. This is going to give me 1 over 4 pi of F beta nu, F beta mu. But then again, it will be minus 1 over some 16 pi, and I'm going to have G sub mu nu, F here, alpha beta, F alpha beta. So that in the end, T sub mu nu is equal to 1 over some 4 pi, which is common, F here, beta nu, F beta mu, minus, and this should be 1 over 4, but then G sub mu nu, F alpha beta, F alpha beta. And this gives us the energy momentum tensor of classical electrodynamics. And if you remember again, you can just make reference again to the lectures 1A or 1B and C. And what we obtained for our energy momentum tensor was this. Yeah, of course, in trying to lower nu, it will simply mean, for instance, that I lower it everywhere. And this again will come down. And of course, you can see, but then it's symmetric. That's the beautiful thing about this energy momentum tensor. What we did then was we obtained something that wasn't symmetric. We had to add another object to it to make it symmetric. We could add another object to it because when we do, it will still be conserved. And that was one of the reasons, or the main reason why we said the energy momentum tensor isn't unique, because you can do that. We had to do that because we needed it to be symmetric. And what we obtained was with something with, we obtained something with a chronicle delta. And now here we have a metric tensor. Everything looks almost the same, except again, of course, for the metric tensor. And if you remember then, when I tried lowering, I said, well, if I decide to lower, and now it all depends on how I do this. If I decide to lower, I said this will give me something like, we've done lowering of indices severally in this lecture series, so please permit me if I just go straight to. So in lowering, of course, I could obtain rho. Using the metric tensor, I'll get some rho. But then in the end, I could rename the rho mu, or nu if I like. And then this will be this, and that will be k. Again, because of the fact that this the energy momentum tensor is symmetric, and if you look here very carefully, you will see that this would simply mean that the nu comes over here with k. Like I said, you have to be very careful. And the lowering will require a multiplication of this chronicle delta with a metric tensor. You can call that the Minkowski metric, but in the end, I said it would be better to have it written in this form. Well, we are not just behaving anyhow. The thing here is this. You want to be very careful because if I wanted to calculate the trace of this matrix, the normal procedure is simply to raise one of these indices, which is mu or nu, and of course, which was why in that formula of video, I simply left I simply left the energy momentum tensor in this form. So by contracting, I'll simply make this to be equal to that. But you can take a note that when I say if I contracted nu and mu here, one could erroneously say, well, if nu is equal to mu, this should give us 1. If that is equal to 1, then well, this wouldn't be traceless. But you can see that from this, it will be traceless because if I raise either mu or nu, I'm going to have something like G mu nu. Contracting the 2 gives me G mu nu, and then of course this is equal to 4. Anytime you're contracting the indices on the metric tensor in this form is always equal to the number of dimensional space in which you're working. And especially relativity as it is for classical electrodynamics, we are talking about the 4-dimensional space. So this was why I was being very careful in writing it in that form. So you might be confused with these 2 forms of the energy momentum tensor, which you will find in textbooks. I can't remember whether exactly, maybe Rolich and Jackson actually did the same thing there. You will find also, okay, well, Landau and Lipschitz in their book, Classical Theory of Fields, have it written in this form, and that's what they've got. So you can see in this form also, we have been able to find the energy momentum tensor in a way that is always symmetric. If you look at this expression, and from where we obtain this, you can see that it's always symmetric with respect to mu and nu. We don't need to add any other, what is it called, object to it to make it symmetric. Object to it that, by the way, is inconsequential with respect to the conservation of the energy momentum tensor. Well, at this point, I think even I am famished. And thank you so much for being with me on this series. Hopefully, again, we shall enjoy ourselves having fun with these things next time when we meet.